Hey guys, welcome to STAT 441 at Virginia Commonwealth University. In this lecture, we are learning about confidence intervals for population proportions. So far, we learned about estimating the mean of a population or comparing the means of two populations using the method of confidence intervals. Now let's look at another parameter that is very common, and this parameter is population proportion. So let's say we are interested in estimating the proportion of successes in a population. So you refer back to the binomial distribution. So in a binomial distribution, the proportion of successes is denoted by the letter P. So this is the same idea here. We are trying to figure out the proportion of elements in a certain population with a certain characteristics. Here are a couple of examples. Let's say a quality control inspector is interested in the proportion of defective items produced on an assembly line. Another example, a supplier of heating oil may be interested in the proportion of home in its service area that are heated by natural gas. So one way to find this value is to find this proportion for all possible outcomes, all possible elements in the population. But this might not be practically possible. It will be time consuming and it will be expensive. So to deal with this problem, we will use, again, the idea of collecting a sample from the population and then calculating the sample proportion as a point estimate. So the sample proportion is denoted by P hat. So there's a hat here on the top, and it is the number of successes divided by the number of items in the sample. So Y is the number of observations that we are counting in a sample of size n. This is equivalent to the number of successes out of n outcomes. Then we can still use the central limit theorem here, the approximation of binomial distribution with a normal distribution for a large sample size. And as, again, going back to the binomial distribution, when the value of the proportion is not close to 0 or 1, the shape is approximately symmetric. The mean of that distribution is n times p. So if we have a large size of our sample, and if the proportion is not close to 0 or 1, we are able to use the central limit theorem. So that will also serve as our assumptions for this confidence interval. Okay, so if we have a large n and p hat is not close to 0 or 1, then we have an approximate normal distribution for our sample distribution of the proportion with a mean which is equal to p and variance given by p times q divided by n, where q is 1 minus p, number of failures. Okay, now with that, we can create the confidence interval just the way we created the interval for theta, because we are using the central limit theorems. This time our point estimate is p hat. So p hat plus and minus z alpha by 2, z being the standard normal distribution, and alpha by 2 will depend on the level of confidence. So if we have a, let's say 1 minus a times 100% confidence interval, then our a is 5% or 0.05, and alpha by 2 is 0.025. So z of 0.025 times the standard deviation, which in this case is p hat times q hat divided by n, and then square root of that. So this formula right here will be our confidence interval for proportions. Okay, now to check the assumptions in this case, this is what we will check. We will check to see if we have a large sample, and we can test that by finding n times p hat. If n times p hat is greater than equal to 4, and n times q hat is greater than equal to 4, then we have a sufficiently large sample. Okay, so with this formula and the assumption, here is an example. Stainless steels are frequently used in chemical plants to handle corrosive fluids. However, these steels are especially susceptible to stress corrosion cracking in certain environments. In a sample of 295 steel alloy failures that occurred in oil refineries and petrochemical plants in Japan, 118 were caused by stress corrosion cracking and corrosion fatigue. Construct a 95% confidence interval for the true proportion of alloy failures caused by stress corrosion cracking. Okay, so in this, this is the information we have. We have a Pigday sample of size 295, and out of that, 118 failures are caused due to corrosion. So the sample proportion here is P hat 118 divided by 295, so 0.4. Now, first we need to check the assumptions before we can create the interval. So we will check n times p hat. N is 295, p hat is 0.4, which gives us 118 greater than 4. N times q hat will be, n is again 295 and q hat is 1 minus 0.4, which is 0.6, so 177. So both numbers are greater than 4. Assumptions are good. We can create the interval. So here is what we will do to create the interval. P hat plus and minus z of 0.025. Again, recall this is how we calculated it. It's a 95% interval. So 1 minus alpha is 0.95. That means alpha is 0.05. Alpha by 2 is 0.025. So this is 0.025 times p hat q hat divided by n. So this z of 0.025 we can find using our z distribution table or the t distribution table at the very end, where the degrees of freedom are infinity. That at that point the z and the t will be the same. So z of 0.025 it was 1.96. 0.4 for p hat, 0.6 for q hat, and then we have n. So our interval is 0.4 plus and minus 0.056, which gives us these two values, 0.344 and 0.456. So here is our confidence statement or interpretation. We are 95% confident that the interval from 0.344 and 0.456 encloses the true proportion of alloy failures that were caused due to corrosion. Okay, so that's our estimate for the proportion of failures caused due to corrosion. Okay, now another possibility for proportions, just like what we did for means, we might be interested in comparing two proportions. For example, proportion of defective items produced by machine 1 to the proportion of defective items produced by machine 2. So we have to compare two proportions in this case. So it will be very similar. We have two samples or two binomial experiments. Y1 is the number of successes in the first experiment out of N1 trials. Y2 is the number of successes in the second sample with N2 trials. So N1 and N2 are the sample sizes, and Y1 and Y2 are the number of successes. We would like to estimate the difference P1 minus P2, where P1 and P2 are again binomial parameters, which is the proportion of successes in the population. For each sample, the proportion of successes P1 had and P2 had, Y1 divided by N1 and Y2 divided by N2. Okay, and the formula for our confidence interval is given by this statement here. P1 hat minus P2 hat plus and minus z alpha by 2 and the standard deviation of P1 hat minus Q hat. Again, using the central limit theorem, we have this relation P1 hat minus P2 hat plus and minus z alpha by 2, and this quantity here gives the standard deviation. Okay, so as you can see, it's kind of a weighted average. P1 hat, Q1 hat divided by N1 plus P2 hat, Q2 hat divided by N2 and the square root for the standard deviation. Here again, we need to check if we have sufficiently large samples. So we check for all four. N1 hat, P1 hat should be greater than 4. N1 Q1 hat should be greater than 4. Same for the second sample, N2 P2 hat and N2 Q2 hat should be greater than equal to 4. Okay, so with this, now we can look at an example. A traffic engineer conducted a study of vehicular speeds on a segment of street that had posted speed limit changed several times. When the posted speed limit on the street was 30 miles per hour, the engineer monitored the speeds of 100 randomly selected vehicles traversing the street and observed 49 violations of speed limit. So you have a sample of 149 violations. After the speed limit was raised to 35 miles per hour, the engineer again monitored the speeds of 100 randomly selected vehicles and observed 19 vehicles in violation of the speed limit. So 19 out of 100 after the speed limit is 35. Okay, so now let's say we want to compare these two proportion before the speed limit. So when the speed limit is 30 versus when the speed limit is 35. So we want to create a 99% confidence interval where P1 is the true proportion of vehicles when the speed is 30 miles per hour, and P2 true proportion of vehicles that exceed the speed limit when it's 35 miles per hour. Okay, so here's what we will do. P1 hat is 49 divided by 100, which is 0.49. P2 hat is 19 divided by 100, which is 0.19. We check the assumptions. So all these four quantities are greater than 4. So we can create a confidence interval. Okay, so using the formula P1 hat minus P2 hat plus and minus the alpha by 2. And then we have P1 hat, Q1 hat divided by N1. So that's the first sample. And this is the second sample. Plug in the values and we get 0.136 and 0.464. So really, how do you get the Z alpha by 2 from the table? So in this case, 1 minus alpha is 0.99. That means alpha is 0.01. 1 minus 0.99 is 0.01. Then alpha by 2 is 0.005. Okay, so again, if you go to the T table, look at the very last column where it is the degrees of freedom is infinity, and then you check for T of 0.005 on the top, connect the two, and that gives you your Z alpha by 2. So with that, the interpretation will be the true difference between P1 minus P2 falls between 0.136 and 0.464 with a 99% confidence. Okay, so here again to see which was there a change. So here the lower limit is the lower bound of the interval is positive, and the upper bound is also positive. That means that the total difference is positive. That means the proportion of vehicles violating the speed limit when it was 30 miles per hour exceeds the corresponding proportion in violation when the speed limit is 35 miles per hour by at least 0.136, and then we have the upper bound for the range. All right, so that's all for confidence interval for proportion. Thanks for watching.